So, we're on. Okay, hello.
Hello world.
So my talk will be about a certain relationship which we discovered between cubical and simplicial sets. So joint work with Chris Kapulkin. So, hello. So let me start with the question of what we call cubical sets. So as it happens, we all know what are simplicial sets. So there is a category called delta, with objects being natural numbers and morphisms from M. Well, let's say natural numbers and morphism from delta and delta from M to M. Objects are usually denoted like this, being monotone functions from 0 less than 1 less than M to 0 less than M. So this is the category of simplicial sets, and then of course the category of the simplicial category, and then of course the category of simplicial sets is defined as the category of contravariant functors from delta to sets. So one can complain that this is actually parameterized by the universe, and in type theory one should. In set theory there is a way to use unbounded quantification to define what pre-shapes are without ever mentioning a universe, which is very cool. I actually found this unbounded quantification to be a very cool device. I know.
Naughty but nice, right?
Well, but you can always turn it into bounded one by introducing a universe. It's just somehow it's nice to play with. Anyway, so so this is simplicial sets, and nobody has any doubt as to what they are. Now, with the cubical sets, the issue becomes that we don't have a single canonical choice of the category delta, or which would be then the category cube, which I'll call cube category and denote with the square. But we don't have a canonical choice. So I can, while preparing to this talk and also talking with Chris when we were working on the paper, we came up with some terminology. So there is, we start with one category, which I'm going to define right now. So objects, actually in all of them, objects will be, so objects of all cube categories, which I'll, for now, what was my idea to write for them? Capital C. small b as for a generic cube category. So the objects are always met, but morphisms differ. So morphisms in this particular cube category, so this is one of the cube categories, from M to N are defined as monotone functions from the partially ordered set 0 less than 1 to the power M to the partially ordered set 0 less than 1 to the power M. So what can we say about other choices of cube categories? So I'm calling this one the central cube category, and kind of put it in the center. Now there are sub-central, which are subcategories in this. But subcategories with the same object. And then there are supercentral, what's subcentral? Supercentral is good enough. Are again the categories for which this is a subcategory. And in real life, it hasn't happened yet, but I can imagine there being something which I can call under central if it is a quotient category of this one. Now, again, so in real life there are examples of, well, in the literature I probably should say, there are examples of people working with many different subcentral categories. So the typical names for morphisms are in the central one are, so the names of some important classes of morphisms in the central one are boundary maps. It's when I take this to this by making the missing coordinates to be either 0 or 1s. So there are straight degeneracies or projections which are projections from this to this, determined by an inclusion from a set with n elements into a set with m elements. Now, there are diagonals, and I'm not going to explain what they are. I think it's kind of clear from the definition. There are symmetries. And there are connections. So connection is the simplest example of a connection is 0, 1 square into 0, 1, which takes x, y, either to, there are two connections here, either to mean xy or to max xy. And you can imagine that there are many connections if there are more, if m and n are greater. Now one can consider subcategories generated by various combinations of morphisms, of those different types of morphisms, and that's what actually happened in the literature. So the smallest one typically is boundaries and straight degeneracies. Then one may add either diagonals or symmetries, or diagonals and symmetries. And then one may add connections, or one may add connections, like in part of the work which we did with Chris, the minimal category which was sufficient for our construction consisted of boundaries, straight degeneracies, and one type of connections, either mean or max. It didn't require anything else, which is remarkable because it produces some highly structured object in response. So highly structured and well behaved. I hope to be able to mention that. So all of these are used to define subcentral ones, and there is one supercentral which is what Thierry and Thierry Coquin and his team have been considering a lot. And this is the category where instead of monotone functions, one considers all functions. And this corresponds, geometrically speaking, to adding also a reflection which turns the arrow around. So this is 0, 1. And if I also add a morphism which permutes 0 and 1 points on this one-dimensional object, and then I close it up with respect to everything else, then the ordering here disappears, and what I get are just functions between finite sets. And that's what they have been considering, as far as I understand. Also, I don't think they ever mentioned it in this exact form. Okay, so I will be interested in almost exclusively, or exclusively, I'll be interested today in the central cubical category. So the one which corresponds to all monotone functions from between this partially ordered sets. Now let's introduce the following concept. Let's call a cube category is called well, let's say a subcentral cube category. Just in case, is called algebraic. If it contains the projections the morphisms from M to 1, which correspond to projections in the square, and are PMI for I equals 1 to M form a Cartesian or whatever people call it, a product cone in this category. So in other words, when M is a product of M copies of 1 with respect to this particular set of projections. Now, as soon as so if we define also a very familiar notation for many people, especially in certain parts of computer science, so we define by F the category whose objects are natural numbers and morphisms from M to N are all functions between standard finite sets with M and N elements respectively. Now, among many, so now I want to connect the cube categories, the algebraic cube categories to Laver theories. I want to say that any algebraic cube category is a Laver theory. To do that in a sufficiently rigorous manner, I need to have to choose at least one particular definition of what a Laver theory is, because there is a number in the literature, and the authors, sometimes one would hear something like they're all equivalent, which might well be true with if I choose a definition of equivalence where by definition everything is equivalent to everything else, then everything is going to be equivalent to each other. But so when one talks about some things being equivalent, one really should specify what under what concept of equivalence, and the thing becomes complicated. So instead, let's choose one definition, and the definition which I found most rigid and so at the same time most useful is that a Laver theory is a pair CL where C is a category and L from F to C the functor that A is the bijection 1 the set of objects and B some method of and B L of 0 is initial, and L of standard co-Cartesian squares are these squares are co-Cartesian. This seems to be a definition that works best, and then one can prove various theorems, lemmas and propositions. Then one can actually, then one can provide various constructions from various different definitions to this one. Since it's most rigid, it's usually very easy to go from this one to anything else. But going back requires sometimes some work. So if one chooses this as the central again, then one can put some order into things. So the statement here is if CP is algebraic, then the then there is a unique, not up to an isomorphism, but really and honestly unique functor L from F into CP of. And here one has to list a couple of conditions such that L of 0 is such that L on objects is identity of the set of natural numbers, and L of the usual inclusions are the projections. And such that this, and this, and CP of L is a lower series. So this is in a sense the major reason why cubical sets are good for doing type theory, while simplicial sets are bad. I mean, this is not the only very important reason, but this is the very first very important reason. And the thing is that Lower theories can be interpreted using presentations corresponding to algebraic theories. So, I mean, a typical example of Lower theory is Lower theory corresponding to groups, to commutative groups, to rings, to whatnot. So the way it happens is, I think I can use this space for a moment. When I'm saying it's a Lovert theory of groups, it doesn't mean that the categories are all the category of groups. The category has as objects natural numbers, so it cannot possibly be a category of groups. What it will be in the case of Lovert theory of groups is the category whose objects are natural numbers, and morphisms are homomorphisms between free groups with the corresponding numbers of generators. So one thing, of course, if CB if CB is algebraic, then morphisms from M to N are in a natural bijection with morphisms from M to 1 to the power n, where the bijection is determined by this very same morphisms by IM. Now let me get, yeah, I think that's right. So correspondingly, to describe such a category, I really sort of only need to know the morphisms from M to 1 plus some additional structure on this set. So I only need to know a sequence of sets equipped with some additional structure. So this additional structure is can be described in different languages. One language is abstract clones, going back to Fiore plotting theory paper. Another way of naming the same structure is that it's a relative monad on the inclusion from standard on the factor from F to sets, and there are probably others. So in particular, by the way, notice that the category of the Lovert theory is the opposite to CB in any case. So when we want to directly connect it with Lovert theory, this will be permuted, so it will be morphisms from 1 to M in the category of the Lovert theory. So if I wanted to do it with the category of groups, I would get homomorphisms from a group on one generator to group of M generator, which is the same as the set of elements of the group of M generators. So I would so these sets will be the carrier sets of free groups with M generators, and then you can imagine that some additional structure should exist on them to tell us that there is a notion of a homomorphism. So the most important for us example of an algebraic category of cubes is the category, so lemma 2, the category is algebraic. So the central cube category is algebraic. It's algebraic, basically, where are the formulas? So the formula is here. So we see that the monotone functions from here to here is the nth power of monotone functions from here to just 0 less than 1. And this is this formula. It is algebraic, and one can ask what kind of algebraic. Is there can we find a familiar presentation of this Laverre theory? Because when we say that groups can be written as through their axioms, it's actually presenting the Laverre theory as being generated by finitely many operations of certain sort. So there can be different presentations, as we know that there are different sets of axioms for what a group is, for example. And but when we're given a Laverre theory, we may ask the inverse question: can we find a convenient presentation for it? And that is it actually something which we know about? And indeed it is. It's a Laverre theory, so it's algebraic, corresponding to the theory of bounded distributive lattices. So this set, which determines everything, can be viewed as a set of our expressions in the free bounded distributive lattice with n generators. So that means, and then if I want an element from this set, that is just n such expressions. So a morphism is just n expressions written in the language of bounded distributive lattices. Which means that I have an excellent, and composition actually is determined by substitution. So we see that we have an excellent way of dealing with morphisms in this category in the syntactic manner. So we can describe this category by syntactic means as a rewriting system for very, very familiar to both mathematics and computer science stuff. And that makes working with it in kind of, if we want to somehow combine this homotopy theory of these cubical sets with type theory, which is what Kapulkin and his group have done. So this gives a way of combining actually two syntactic gadgets, as opposed to combining something syntactic, like type theory, with something which is entirely not syntactic, like delta, because delta is never, delta, the simplicial category, it's not algebraic. It does not correspond to any algebraic theory. Not in this way, so it's difficult to work with, basically. While here we can, I'm going to give some demonstrations later on by writing these expressions in distributive lattice. So okay, so that's an explanation why, the first reason why cubical things are so more convenient to deal with in the context of syntactic work than simplicial.
And a question, so with Kapulkin's stuff, they're adding a reverse, right? And you get De Morgan algebras instead of distributive lattice. So is it the case that that's not worth, as it were, doing? I mean, because you don't really need to do it. I mean,
I'm yet to see a situation where that would be useful.
yeah, okay. That's
So,
interesting.
I mean, we'll see that having to choose the central one, which comes with a full embedding into this monotone set, is really will bring some really nice stuff in a few minutes. But what would be added by forgetting about the order, I don't know. So, okay, so that was. I was actually wondering if one can make delta kind of algebraic by using something like dependent in essential algebraic theory. The problem is that the variables in delta, so these elements of the set from 0 to n, they are ordered. So what if if there are just variables where each variable has a type of my kind of algebraic thing, there is no reason to order them. I mean, if okay, I'll skip it fast. So, what about we try to add dependencies between them so that we cannot reorder them? We are not going to get delta because the C system of or kind of the contextual category of such a type theory is still going to have products. But we may get the closure, the product closure of delta, the finite product closure of delta in simplicial sets. Maybe well, that's purely a matter for kind of for users. Okay, so. So all this is known. I was just trying to also put some kind of order in it. Now what we are going to do is the following. So we'll have S set, the category of simplicial sets, and we'll have C set, the category of cubical sets with respect to the central cube category. We are going to construct a full embedding U from simplicial sets to cubical sets. And we're going to construct a left adjoint T to this full embedding, which is left exact. And moreover, we're going to explicitly describe a topology on the category of cubes such that this embedding is an equivalence between simplicial sets and sheaves in this topology on the cube category. So, for simplicial, cubical sets are free-sheaves, simplicial sets are sheaves. And then I'll give a few examples. So that's the first relationship. So we start with functor little t from the central cube category to the category of simplicial sets, which is going to be a full embedding. And actually I'm sorry, I have my okay, so this functor takes n into delta one-dimensional simplex to the power n. And it's easy to see that this functor indeed is a full embedding, because our morphisms in cube from m to n are the same as monotone maps from 0 m to 0 1 n, which is the same as functors from the category 0 goes to 1 to the power m, and 0 goes to 1 to the power n, which is the same as morphisms in simplicial sets from the nerve of this category to the nerve of this category, as is well known. And the nerve of this category is our delta 1 to the m, and this one is delta 1 to the m. So that's a proof. Now we can use this I wonder if there was some mix-up between U and T in the text which I had. So I may at some point say no. Let's rename U into T. But let's define U simplicial. Well, it says here simplicial set into cubical set. Well, the idea that this is in kind of the simplest example of a cubical set, and this goes into simplicial. So that should be called T, because this is a little t. And then from simplicial to cubical, let's call it U. So if I have an x here, I will map it to the functor, which maps n into morphisms in simplicial set from little t of n into x. So this is kind of the obvious functor which one would expect from having a co-cubical object in a category. We get a functor from a cubical object, from the category to the cubical object. It has some obvious properties, such that it commutes with limits and with filtering code. Now I'll need a couple of more construct statements. So So I'm going to prove that U is a full embedding that I'm going to construct a topology on C set such that U is an equivalence on a topology on the cube category such that U is the inclusion from sheaves to pre-sheaves. And then T will be the factor of associated sheaf. And I'm going to do it in 2 steps, both of which will I'll have to refer to. So for so let G be the topology one pre-sheaf. Well, in our case, it will be pre-sheaf of the our cube category, but in general, on any C, I'll start doing something first with general C and D, and then we'll specialize to this. So the topology on this whose coverings are jointly surjective families. So because pre-sheaf has nice properties such a pullback of an epimorphism is an epimorphism, I should say jointly epimorphic families. This is really a topology, otherwise I would have to do some extra moves. Then, so my lemma, what the number was supposed to be 3, is going to be that the functor from pre-sheaves on C into sheaves on pre-sheaves on C with respect to the topology J is an equivalence. So the functor here is we take uneta, and then if we are unlucky and for some reason representables are not sheaves, which they're going to be, but we don't even care, then we just take also functor of associated sheaf. Now, one can say that there is a bit of cheating in this, because if C is small, this is locally small, and this guy is large. However, if we work with, let's say, a hierarchy of 2 universes, it is true that that this will be a large category, while this will be a locally small category, but there is nothing wrong in them being equivalent, especially if I understand equivalence in some constructive way. It is fact, if I understand correctly, that in unimass, using one of the resizing rules, one can actually place this category into the type of locally small categories, just using this equivalence and the resizing rule. So that might be one of kind of more a new use for resizing. So this is known, and one of the references is SG1 theorem 4.1. Now I want to have lemma 4, which says the following: that let D to pre-shift on C be a full embedding. Full embedding, I mean a fully faithful function. Such that for all x in C, there exists y in D, and a retraction from, this will be functor f, from f of y into uneta of x. So any representable is a retract of something which is in the image of this function. Then the functor, which I'll have to specify, shift, pre-shift, C, G into shift when D F upper star of G is an equivalence. Now, what's written here is the following. So we have a functor from D to pre-shift, it doesn't matter, to some other category, and we have a topology on that some other category. Oh, okay. Yeah. Then I can pull back this topology to the source of the functor, and then I will have a functor from shifts on the target category in my topology into shifts on the source category in the pullback. And if this condition is satisfied, then it is an equivalence. So this is a very particular case of something which is called comparison. No, actually, excuse me. I was giving a wrong reference. So this is SG1 theorem 4.1, and the reference for that statement is should be something different. So Chris found the reference in Mackay and Ray's first order categorical logic, but I also know that there is there are much earlier references, and it's not such. So excuse me, it was a slightly different reference. So now consider, let's take Z being the cube category, C being the delta category, and F being our functor little t. So we know that F is a full embedding. So we need to check this. So F of n, well, actually I should start with x. So your net of x is delta n. Your net of n is delta n. It's a standard simplex. F of n is delta 1 to the power n. There is a projection here which has n factorial different sections. Because the n-dimensional simplex can be seen as it's a symmetric power of delta n. So it's actually a quotient of delta n to the n by the action of the symmetric rule. And because delta n is a projective object in the category of simplicial sets, this projection has a bunch of sections. Okay, so now I'm running out of my time. And do we have a break?
Yes. Well, I mean, enough for Benedict to set up, but.
Yeah, I was wondering if I can get kind of 5 minutes from Benedict.
I think he's probably not in a position to say no. So yes.
Well, especially since what he will be giving a talk about also.
Let's say yes.
It's also a joint work with me, so I'm also taking 5 minutes of.
Every minute we negotiate is a minute less for you.
So the condition is satisfied, and so we have we can apply the composition of these two lemmas, and we'll see that the presheaves on delta, which are simplicial sets, are the same as presheaves on simplicial sets in this topology J, are the same as our sheaves on D in this topology F upper star of J. So what I wanted to do was to say, can we describe this topology explicitly? And of course, what I wanted to say is that we can. First of all, I'm going to call it delta topology. So delta topology is this topology shifts with respect to delta on the category of cubes. Shifts with respect to delta topology are simplicial sets. So one can show that a family. So here I have Mi mapping to n. That all happens in family of morphisms in the cube category. So that this is a delta covering if the disjoint union of C of Fi, so that will be a disjoint union of delta 1 to the Mi and I mapping into delta 1 of n, but now there are simplicial sets. So if this is a surjection. Let's say it's a surjection is the right word, I suppose. Yeah. is a surjection. So alternatively, there are n factorial n-dimensional simplices there, and if for every one of these n factorial simplices, one can find a preimage in among one of these, then it's a covering. Otherwise, it's not. And that is an explicit definition of the delta topology. And what I can do also is to give an example of something which is not a sheaf. So a cubical set which is not a simplicial. And but even before doing that, because let's see. First, I'll formulate the question, which, in a sense, can be the raison d'être for this talk. So the question is the class of delta sheaves closed under gluing. So the thing is that if yes, then we of course can have gluing in simplicial sets, which would be unexpected and remarkable. If not, then we're going to have a very good example explaining exactly what goes wrong. So where the gluing construction takes us out of the simplicial sets, because kind of all the starting points are usually simplicial sets. So the cubes themselves are delta sheaves. They correspond to simplicial sets, which are just delta 1 to 0. There are many. If one starts putting cubes together in some kind of geometric way, one will continue to be inside delta sheaves, because then you just triangulate and you obtain the simplicial set, which corresponds to your cubical. Here is an example of how to get something which is not. So we had that delta n, and here was cube n, and there was this projection. And it had a bunch of sections, so there are also the inclusions from here to cube n. So so there are n factorial different inclusions, and what we get actually is one can verify it. We get n factorial projectors on the cube in the cube category, and we should be able to write them down explicitly, because we know that functions from here to here are given by each function is a sequence of n expressions in n variables in the language of bounded distributive categories. So in particular, we have the example of 2. So these are two inclusions. This is the cube. And this is intuitively the two inclusions corresponding to this index. Now, how to describe this function? I mean, there are two versions, and we should be able to see how to do both. So if x and y are my generators, then one triangle corresponds to the function x plus y, x times y, and I just write plus and times for the. And of course, another one corresponds to them permuted, because that's what it's supposed to be. It's just the order in which we list these expressions, this factorial version. So one can compute and verify that it's indeed a projector, for example. It's obvious that it's invariant intersection of symmetric group in two variables, but the fact that it's a projector. So I haven't entirely checked it, but my understanding is that if we go to the dimension 3, then we are going to get the standard symmetric functions and so on.
Are those the operations of the lattice, the join and the meet?
Yeah.
Plus and
Yeah.
minus?
Yeah.
Your 5 minutes is up, by the way.
I'm almost there. So this is a retract of a sheaf. And so a retract of a sheaf is a sheaf. So this is a sheaf. Of course, it's also a sheaf because it's delta 2. So how to do something which is not a sheaf? So the simplest example I know is one should take this delta 2 and this delta 2. So let's call it A and this. So these are sub-objects in the two-dimensional cube. And then I want to take their union, not disjoint union, but their union as sub-objects of the square. So this is going to be a sub-object in two-dimensional cube. When you take associated sheaf, it's going to become an isomorphism, because these things will just become the simplices themselves, and this will become a union of two simplices, which is equals to the to this square, triangulated square. However, in the cubical sets, it's not an epimorphism, because the main square cannot be lifted to either I or B, A or B. And squares are projective objects, so any surjection to a square should have a section. And here we don't have a section. We can write it further and kind of play around with it and see that how to describe this union again algebraically. And one way to describe it algebraically is that f plus g equals f, or f plus g equals g. So f and g here, what I'm trying to describe, it's sub-object in delta 2. So I need to describe, specify all the functions from delta k to delta 2, which are factorized through this sub-object. So functions to here are pairs of expressions in k variables, which I called f and g. And one can show that they factorize through this if either this holds or that holds. So again, this is an example how one can compute using algebraic nature of the cube category with kind of geometric or that's sheaf theoretic things. Thank you.